Alright, so I guess I need to also guide you through this another example. Um, it's for the frame analysis. Okay, so again, we are referring to the tutorial document provided in the website. So first, let's set up the grids. Okay, so modify, then grid. So here we have actually two intervals at 20 along the x-axis, and along the y we have one interval at 10, and then another one interval at 9. Okay, so let's click OK, and then you'll see that. So the next thing is we'll set up our joints. So the joints, we have joint A, and our x is 0. The location of the joint A is x 0, 10. Okay, for joint B, we have 20, 10. Oh, sorry. Okay, B, then 20, 10. Sorry. Okay, and then for our joint C, we have 40, 10. And then joint D is 40, 19. Okay, what else? DE. Okay, so our joint E is 40, 0. Then point F, that's 20, 0. Okay, so that's our joint. Then we'll set up our boundary conditions. So the joint A is a pin support, so meaning that the X is there's a reaction, it's a fix at X, and there's also a reaction at along the Y. Rotation, there's none. Okay, then the next is joint, um, let's say joint D. So the joint D, that's a roller support. So a roller support with a reaction along the x-axis. Okay, and then the y it's free, and then rotation is free. Next for the joint E. So for joint E, it's a fixed. So we can just select this fix, and then check this selection. Set the boundary codes for all the directions. So take note, we are referring to the x, y, and then the z. Okay, and then for letter F, we have also a fixed support. Okay, so that's it. Okay, so you can see that we have the spin, the roller. So let's turn on the label. So we have the spin, roller, fixed, and fixed. Okay, so now let's draw the members. So again, you can input the data in this spreadsheet, or you can just do this graphical approach. So we have this member properties that we need to input. So it says in page 12, it says that our value of I of our moment is inertia is 500. The area of member AB is 15, so let's input 15 inches squared. And then the moment of error is 500. But take note that in the problem, the member AB, the member from A to B, is 2I. So meaning that we have a 1000 inch to the fourth. Okay, and then the Young's modulus is 29,000 KSI. Okay, so we'll select this fixed, or probably pin. Okay, well, we'll just check first. Fixed. Okay, so fixed, and then fix. Okay, so that's our member 1. Then for our member 2, it says that, okay, so we'll click this again. We have an area of 10 inches squared. So 10 inches squared, and then the moment of inertia is just I, which is 500. Okay, so the B is fixed, fixed. Okay, so fixed. I mean the member B is fixed, is this one. And then the member 3 is this member from B to F. So let's click this again. We have our I would be fixed, and then the F would be fixed. Okay, so try this. And then member 4, that's member CE or members EC. Then for member 5, okay, that's fixed. Okay, I think we'll try this pin at this point. Okay, we'll check. We can edit if we want. So for our member 5, so you can also view or turn on the labels. Okay, so for member 5, let's say this is our first and this one is the last. So we'll edit. Let's say this is pin. Okay, pin. And for the member 1, for the this pin support or pin boundary conditions, now we'll check if this is pin. Okay, so the I is pin. Okay, and the next one is, since we're done with our members, then we can specify or construct our loads. So we have joint. No, I think there's no joint loads in the problem. It's just distributed loads and point loads. So the difference again is the joint loads refers to the loadings of the joint, whereas the point loads is a loading on the member, but it's a concentrated loads. Okay, so point loads. So we have a point load of 32 kips. Okay, so we'll click this, or we can also, by the way, you can also construct the boundary conditions in terms of this. You can just select free, fixed, paint, or roller. Okay, so anyways, so let's go to the point loads, or here. Okay, so point loads. Okay, so if we'll go for these spreadsheets, then our point loads would be in what member will that point load exist. So it's in member 2. And then what's the direction? There's a vertical load, so that's y direction. Then the magnitude is, since it's downward, then that's negative 32. And the location is, we're actually given a dimension, or a dimension of 20 feet, but the location of the point load is just 10 feet from this point C. So even if our reference point is B, then that's gonna be 10 feet. Okay, so meaning the location of this corresponds to the location relative to this member. Okay, so we'll we'll input 10 because that's 10 feet. Okay. Okay, I guess we'll just select this one. Click this point loads. Okay, so point loads again. So the magnitude is negative 32, and the location again corresponds to the relative position. So that's 10 feet. So let's click apply, and then this is our. I mean the point corresponds to this target. Target. symbol here. So if we select this M2, then that's where the load will appear. Okay, so that's it, 32. Okay, so we'll delete this one. Okay, the next thing that we'll do is the distributed loads. Okay, so distributed loads, we'll just click here. Then what's the direction? So by the way, for distributed loadings, you can also have the equivalent. Let's say you have a wind load along the roof of a portal frame. Then it can also translate the values like in terms of the vertical or this probably I think that's the lateral. Okay, so you can explore this for our problems in portal frames. Okay, so start magnitude. What's the magnitude? That's negative 3.6. So you can also, I guess you can also do like varying loads. Okay, so start location. So we are starting from this joint A and then ending up at joint B. So that's 0, 20. Okay, so apply. Then just click like that. Okay, so now once we're done, then we can solve. Okay, so click solve. So if you click solve, then we can check if what we did is correct. Okay, so we can view the support reactions. Okay, let's just view the moments, the moment diagram. Okay, so this is our moment diagram. Okay, so if you check it in figure 30, we have a 114 maximum 0.5, and then we have a 39.6. Then we also have 18.8. Okay, so this is an 18.8. Except that this is positive, so well, probably I think we should do when drawing up the members that from down to up. Okay. Okay, negative 27, 28.9, negative 13. Okay, so we'll check. Member 30. No, member 3. So that's B to F, or we'll just write F to B. Okay, we'll try. Okay, F to B. Okay, so let's click solve again, and then okay, so that's it. So from left to right or up, I mean from bottom to the top. Okay, so we have 39.6, okay, 78. So I guess so far so good. You can also check the deflections if you'd like. Okay, so that's the deflections. Now for printing, we'll try this. So file, or you can just click this. Okay, so let's say portrait. So what's the scale factor for the printing text? Okay, page setup. Okay, print a report instead. Okay, so we can select if it's let's say joint coordinates. Okay, so member forces. Let's try joint reactions. Okay, we'll just try this. Okay. Okay, so that's the printed output. Okay, so if you have input your the designer here, then your name will appear here. So we have the joint coordinates, reactions, member forces. If you select 5 sections, then that's the value. All right, so I guess that's all, and um, I have included a lot of samples or homeworks so that you can practice using this software. Okay, so in the next video, we'll move on to our next topic, which is the structural loads. All right, so see you in the next video.